In the vast expanse of our solar system, discoveries continue to amaze us. Among the many wonders that orbit our sun, the gas giant Jupiter and its retinue of moons stand out. In 2001, a team of astronomers led by Scott S. Shepard made an exciting find, a new moon orbiting Jupiter. This tiny world, initially designated S2001J4, would later be named Euporie. The discovery of Euporie added to the already impressive number of Jovian satellites. It highlighted the incredible diversity and complexity of our solar system. This tiny moon, with its unusual orbit and intriguing name, offered a new puzzle piece in our understanding of Jupiter and its surroundings. Euporie is a small moon, even by the standards of Jupiter's outer satellites. Discovered in 2001, it is one of the many irregular moons that orbit the gas giant. These moons are thought to be captured objects, possibly asteroids or remnants of larger bodies that broke apart. With an estimated diameter of only 2 kilometers, it is dwarfed by the 4 Galilean moons, which are visible even with small telescopes. These larger moons, such as Ganymede and Callisto, are massive in comparison, each with their own unique features and atmospheres. In fact, Euporie is so small that if you were to stand on its surface, you would be able to see its curvature against the blackness of space. This tiny moon's weak gravity would make it a unique experience, as you would feel almost weightless, able to jump great distances with ease. Despite its small size, Euporie is a fascinating object. Its irregular shape and rapid rotation make it an intriguing subject for astronomers. Observations suggest that it completes one rotation every 12 hours, which is quite fast for a moon of its size. Its surface is likely a dark and heavily cratered landscape, shaped by billions of years of impacts from asteroids and comets. These impacts have left a record of the solar system's history, with craters overlapping each other, telling a story of constant bombardment. Its low gravity means that it is unable to hold on to an atmosphere, leaving its surface exposed to the harsh radiation environment surrounding Jupiter. This lack of atmosphere also means that temperatures on Euporie can vary dramatically, from extremely cold in the shadowed regions to slightly warmer in the sunlight. Additionally, Euporie is constantly bombarded by Jupiter's intense radiation belts. These belts are part of Jupiter's powerful magnetosphere, which traps charged particles and creates a hazardous environment for any object within its reach. Euporie's orbit is also quite eccentric, taking it far from Jupiter at its furthest point and bringing it closer at its nearest. This elliptical orbit suggests that Euporie may have experienced gravitational interactions with other moons, or even with Jupiter itself, altering its path over time. In the vastness of space, Euporie may seem insignificant, but it holds clues to the dynamic processes that shape our solar system. Each small moon like Euporie adds to our understanding of the complex gravitational dance that governs the movements of celestial bodies. One of the most intriguing aspects of Euporie is its unusual orbit. Unlike most of the planets and moons in our solar system, which orbit in the same direction as the sun's rotation, Euporie's orbit is retrograde. This means that it orbits Jupiter in the opposite direction. This retrograde orbit is a telltale sign that Euporie did not form in its current location. Astronomers believe that it was once a free-ranging object, perhaps an asteroid or a comet, that was captured by Jupiter's powerful gravity. The capture process likely disrupted Euporie's original orbit, sending it into its current retrograde path. Euporie is not alone in its retrograde orbit. It is a member of a group of Jovian moons known as the Ananke group, named after the largest moon in the group. These moons share similar orbital characteristics, suggesting that they have a common origin. The Ananke group is thought to be a collection of captured objects, likely remnants from the early solar system. These objects were likely scattered into the outer regions of the solar system by the gravitational influence of the giant planets. Some of these objects were eventually captured by Jupiter, forming the Ananke group we see today. Section 5, the Kozai mechanism, a celestial tug-of-war. The retrograde orbits of Euporie and the other Ananke group moons are not static. These moons, which orbit Jupiter in the opposite direction to the planet's rotation, are in a constant state of flux. Their orbits are influenced by a variety of factors, making them dynamic and ever-changing. They are constantly being perturbed by the gravitational influence of Jupiter and the Sun. Jupiter, being the largest planet in our solar system, exerts a tremendous gravitational pull on its moons. At the same time, the Sun's gravitational force also plays a significant role, creating a complex interplay of forces. Over long periods, these perturbations can have a significant effect on the Moon's orbits. The gravitational tugs can cause the orbits to shift, sometimes dramatically. This ongoing process can lead to changes in the shape and orientation of the orbits, making the study of these moons a fascinating subject for astronomers. One such effect is known as the Kozai mechanism. Named after the Japanese astronomer Yoshihide Kozai, this mechanism explains how the gravitational interactions can lead to periodic changes in a moon's orbit. It's a key concept in celestial mechanics, helping scientists understand the long-term evolution of orbital systems. This mechanism describes a cyclical exchange of energy between a moon's orbital inclination and its orbital eccentricity. In other words, the tilt of the moon's orbit and the shape of the orbit itself can change over time. This energy exchange is a delicate balance, influenced by the gravitational forces at play. In simple terms, this means that the moon's orbit can become more elongated or more tilted over time. An orbit that was once nearly circular can become more elliptical, and the angle of the orbit relative to Jupiter's equator can shift. These changes can have profound effects on the moon's behavior and its interactions with other moons. The Kozai mechanism is thought to play a role in the long-term evolution of the Ananke group moons, potentially even leading to collisions or ejections from the system. As these moons' orbits change, they can come closer to each other, increasing the likelihood of collisions. In some cases, a moon might be ejected from the system entirely, sent off into space by the gravitational forces at work. This ongoing celestial dance is a testament to the dynamic and ever-changing nature of our solar system. The name Euporie has its roots in Greek mythology. In Greek mythology, Euporie was one of the Horai, the goddesses of the seasons and natural order. She was the daughter of Zeus, the king of the gods, and Themis, the goddess of divine law and order. Euporie's name, meaning abundance or fertility, reflects her association with the bounty of nature. The choice of this name for a Jovian moon is fitting, as Jupiter, the Roman equivalent of Zeus, was the god of sky and thunder, and his reign was associated with prosperity and abundance. Despite its small size and remote location, Euporie holds clues to the history and evolution of our solar system. By studying its composition, surface features, and orbital dynamics, astronomers can gain a better understanding of the processes that shaped the Jovian system and the outer solar system as a whole. Future space missions, equipped with advanced instruments, could provide valuable data that would shed light on the mysteries surrounding Euporie. These missions could analyze its surface composition, map its geological features, and study its interaction with Jupiter's magnetosphere. The discovery of Euporie and other irregular moons like it has challenged our understanding of how Jupiter's moon system formed. These moons, unlike the regular ones, have peculiar orbits that don't fit into the traditional models of moon formation. Their existence raises questions about the processes that shaped the early solar system and the dynamic environment around Jupiter. The traditional model suggests that the regular moons, including the Galilean moons, formed from a circumplanetary disk of gas and dust that surrounded Jupiter in the early solar system. This disk, much like the protoplanetary disk that formed the planets, provided the material for these moons to coalesce and grow. The Galilean moons, Io, Europa, Ganymede, and Callisto, are prime examples of this process, showcasing relatively circular and coplanar orbits. However, this model cannot explain the existence of the irregular moons, which have highly inclined and eccentric orbits. These moons, including Euporie, Carpo, and others, follow paths that are significantly tilted and elongated compared to the regular moons. Their orbits suggest a different origin, one that involves more complex gravitational interactions. The capture scenario offers a more plausible explanation for the origin of these irregular moons. In this scenario, these moons were not formed in place, but were instead captured by Jupiter's immense gravitational field. This process would have involved these objects, which were likely asteroids or comets, being pulled into orbit around Jupiter as they ventured too close. According to this scenario, these moons were once independent objects, such as asteroids or comets, that were captured by Jupiter's gravity as they passed too close. This capture process is thought to be highly chaotic, involving complex gravitational interactions that could significantly alter the orbits of these objects, leading to the diverse range of orbits we observe today. The capture process would have been chaotic, resulting in the wide range of orbital inclinations and eccentricities observed among the irregular moons. This chaotic nature of capture means that each irregular moon has a unique orbital history, shaped by the intricate dance of gravitational forces. Understanding these processes not only sheds light on the history of Jupiter's moons, but also on the broader mechanisms of planetary formation and evolution in our solar system. Euporie, a tiny moon in the vast expanse of space, serves as a reminder of the endless wonders that our universe holds. Its discovery has expanded our understanding of Jupiter's moon system and challenged our theories about the formation of planetary systems. As we continue to explore the cosmos, we can be certain that new discoveries await us, each one adding to the rich tapestry of our understanding of the universe and our place within it.